This is going to be an introduction to integrals. Now you've already seen this in a special case in that section on the logarithm. And now I'm going to just do a more general treatment of it here in this sequence of exercises. And then in a later chapter we will discuss the relationship to the Riemann integral. What I'm going to present here is the Darboux integral. There's a lot of background to integrals, really. So let AB be an interval. It's a closed interval always. And we're going to look at a sequence of points where x0 is equal to a, and then it's smaller than x1 up to xn equal to b. This is called a partition of the integral. Now suppose f takes ab to r is a bounded function. Let m sub I be equal to the supremum of f of x such that x is in this closed interval and little m sub I is the infimum. Then the upper sum is defined as capital M sub I times the length of the subinterval. That's called an upper sum. L of f comma p is the lower sum. So I put little m sub I, lowercase m sub I, times the length of the subinterval. That's a lower sum. And what I want to do is show that if you have two partitions such that p is contained in Q, then the upper sums get smaller and the lower sums get bigger. So essentially what is happening is, at least in case f is positive, what happens is the lower sums, as you get more points in the partition, the lower sums do a better job approximating the area under the curve. The upper sums also, as you increase the number of points in the partition. Now the way to understand this is to add in a single point and see what happens. So here I have a function, and what happened here is this, and this would have been a lower sum approximating this material underneath this graph of this function. Now when I add in another point z between x2 and x3, what happened was now I added in this gray area, and so you see the lower sum got larger. Similarly, the upper sum got smaller by this amount. Okay? So whenever you add in a point, the upper sums get smaller, the lower sums get larger. And so that brings us to the next problem. If I have a couple of partitions, P and Q, and I look at the upper sum with respect to P, it's bigger than or equal to the upper sum with respect to P union Q, because you see I can just add in all of the points I need to this partition until I get to P union Q, and each time I add such a point the upper sum gets smaller. So this is true, and now you know that for a given partition the upper sum is obviously bigger than or equal to the lower sum, and now by the same reasoning the lower sum here is bigger than the lower sum here, because the lower sums get bigger as I put more points in the partition. Alright, so what does that say? That says that if I define I with a little bar on the top as the infimum of all the upper sums, and I will define I with a little bar on the bottom as the supremum of all the lower sums, it follows that I lower bar is smaller than I upper bar. When these are equal, we say the function is integrable, and we write this for the common value. Okay? So what I need to do is show this. Well, I think we just discussed this inequality. Okay? Now I want to look at this. I bar is the infimum of all these. What I know is that each of these upper sums is bigger than a particular lower sum. Okay? So if I take the infimum of all of these upper sums, it's bigger than or equal to this particular lower sum, because this, after all, is a lower bound. So the greatest lower bound uh, um, is at least as big as this. Okay? So I have that this happens. And now you see I have I upper bar is an upper bound for all of the lower sums. So if I take the supremum of all the lower sums, I get I lower bar. So you see this inequality always holds. I upper bar is bigger than or equal to I lower bar. Always is the case. Okay? So, sometimes they're equal, and sometimes they're not. When they're not, the function is not integrable. Now, when we discuss this more in the chapter on the integral, I'll give examples, but you might try one such. Consider the function which is 1 on all the rationals and 0 on all the irrationals. Write down upper sums and lower sums, and you will see that there's always a gap between them. Go ahead and use the interval from 0 to 1. Okay, show that any decreasing function is integrable. Well, how am I going to do that? I'm going to try and show that there's no gap between the upper integral and the lower integral. That's what I'll call these, okay? So if I take this minus this, it's smaller than that. Now, why is this? Well, and where are these coming from? I'm just going to go ahead and let them be equally spaced so that the distance between any pair of these, any successive points, is equal to b minus a over n. Okay? And now what I'll do is I'll notice that the upper sum is here. So I know that this is bigger than or equal to that. And the lower sum is here. And that's smaller than or equal to that. So this difference is smaller than these. Well, if I look at what I've got here, I get this. Factor out this b minus a over n. And now this sum is equal to f of a minus f of b. And so this is just some number. Now, the gap between these is smaller than some constant divided by n, and n is completely arbitrary, so that tells me that the gap between these two numbers has to have length 0. So they're really the same number. And that shows every decreasing function is integrable. Now, the next problem involves observing that any reasonable function will be integrable. Now, by reasonable, I mean one that is like what follows. You have a bounded real-valued function and a partition such that on each of these subintervals, f is either increasing or decreasing. In other words, f is not infinitely wiggly. Okay? Show then that the integral exists. Okay, similar reasoning applies to the above that we just used above, applies to increasing functions. So you can just write down the difference between the upper sums and the lower sums and then show it goes to 0 in exactly the same way. You just would turn these around. You'd have an f of xk here and an f of xk minus 1 here. And you'd still have everything work out the same. Okay, so what I know is that pertaining to each of these intervals, the integral, the upper integral and the lower integral, there's no gap between them. So there is a upper sum and a lower sum for each of these, where their difference is smaller than epsilon over n. All right? And so now, if I use those upper sums and lower sums and use for the partition the union of all the partition points associated with each of these subintervals, then the upper sum minus the lower sum will have to be less than the sum from k equal 1 to n of epsilon over n, and that's just epsilon. Alright, so therefore there's no space between these two since epsilon is arbitrary. Now here's another important observation. If you have a function on an interval, and b is somewhere between the two endpoints, and if you know this function is integrable on these subintervals, then it will be integrable on the whole interval. And in fact, I can say the integral from a up to b plus the integral from b up to c of f is the integral from a up to c. Okay, this is just like the above problem. There's a partition P1 of AB, see, a up to b, and one for b up to c called P2, such that u of f P1 minus L of f P1 less than epsilon over 2, and same with P2. So what I'll do is I'll let P be the union of these two partitions, and now what that will do is that will give me a partition of the whole interval from A up to C. And then this minus this would be equal to this one minus this one plus this one minus this one. All right, and so it would be less than epsilon. And so there's no space between these upper and lower integrals. So the function is indeed integrable on the interval from a up to c. And also, I need to now verify that this identity holds with the integrals. Well, I know that this is true, and so minus epsilon is less than this minus this, which is equal to the sum of these two lower integrals minus this upper integral. And now the lower integral is smaller than it should be for this, so I'll replace this one with this one. I'll replace this one with this one, and things got bigger. And then the upper integral is too large, so I'll replace with something smaller, and that will make the whole thing larger. And then this one is smaller than this one is smaller than this one, and this one is larger than this one. So I get this, and that's equal to the difference of these, which I chose to be less than epsilon. So what does that say? That says that this expression here is somewhere between minus epsilon over epsilon, and epsilon was completely arbitrary, so the only thing this expression can be is 0. So that shows you the very important property of integrals, that you can split them up across an interval. Now what we haven't discussed is what happens when you have an integral from b up to a where b is bigger than a. Well, the way we define it is as negative the integral from a up to b. So the observation here is that you can always write this. Okay? So what I want to do is consider the case where a is less than b less than c. That was just done above here. So now I'll suppose that I switch c and b, and that c is smaller than b and bigger than a. Then what was just done is I can say that this is equal to that. And so now what I will do is I will take this over to the other side. I will subtract it like this. And now, from the definition, you see you have c is smaller than b, and if I switch b and c, I would change the sign, and I get this. So you see, algebraically it works exactly the same way. And various other cases can be considered. You see, you could have b less than a less than c, and it would all work out exactly the same. And that's about all we have to do for the integral. So that completes this chapter.